we have our first presentation from ReWiND. The floor is yours.
Thank you. Hi, my name is Zhang. This is Abrar Anwar, and we're here to talk about our work, ReWiND, Language-Guided Rewards Teach Robot Policies Without New Demonstrations. To get an intuition of our approach, let's start with an example. So imagine you wanted to play basketball. Having done my PhD in Los Angeles, I'll use the Lakers for inspiration. You'd see amazing NBA stars like Kobe Bryant or LeBron James. A natural question to ask is, how does one get to being this good at basketball? Well, it starts with having a great coach. Many great coaches share 3 core traits. They provide detailed feedback when you make mistakes. They generalize their guidance to various basketball skills needed to play at different skill levels, whether it's in college, on the streets of Seoul, or all the way to the NBA. And they adapt their teaching style as your own play style evolves. Skilled coaches are necessary for basketball players to master every skill needed in basketball. Now, what would a skilled coach look like for robotics? In robotics, a coach, or maybe more generally, a teacher, is like a reward model. Just like a great coach, a reward model should enable our robots to learn new tasks by providing detailed feedback, even under policy execution failure, generalizing to unseen tasks so that the robots can learn new things, and of course, being robust to how the task is specified or performed by the robot. The challenge is, how can we train such models scalably so that they don't need a lot of successful and failed demonstrations for every new robot setup? Keeping in mind our 3 desiderata, we address these challenges with ReWiND, rewards without new demonstrations. The goal here is to train a reward model that enables a robot policy to learn unseen tasks just from language. To do so, ReWiND requires just 5 demonstrations per training task. After a human collects these language-labeled demonstrations, we then train a data-efficient reward function and offline reinforcement learning policy on the demos. We then deploy the policy to directly learn an unseen task with online RL and dense rewards coming from this language-conditioned reward model. This results in real-world learning of unseen tasks in just 1 hour.
Given only successful demos without reward labels, we use a simple and stable progress prediction objective to train the reward model. For example, in this demo of a robot picking up a cup, progress is defined simply as the current frame divided by the total number of video frames. This objective directly translates into a dense 0-to-1 scaled reward for training an RL policy. But only training on successful demos won't lead to properly rewarding failed policy rollouts, which is very important when you're trying to learn new tasks. Therefore, we introduce a video rewinding mechanism that generates failed trajectory examples from only successful demonstrations. Let's say we rewind the trajectory at the 4th frame for 2 steps. Until this 4th frame, the progress target increases, and then we split the video at the 4th frame and predict decreasing targets for the rewound video. This video now looks like a failed demo where the robot drops the cup, and we still have dense reward labels for each frame. Finally, to encourage generalization to unseen tasks and robustness to how the policy solves the task, we additionally train ReWiND on a subset of the OpenX embodiment dataset. Okay, so are these things good enough to get a great reward model? Actually, no. Early on, we found that naively training an autoregressive video reward model still couldn't generalize well to out-of-distribution tasks. So we made specific architectural changes and choices to resolve this generalization challenge. Language and video inputs go through frozen Dino v2 and mini LM embedders and then get projected to a shared space for a temporally masked transformer, which outputs embeddings per frame and is finally converted into a per frame reward estimate. To handle reversible tasks like pulling and pushing, we do need positional embeddings, but giving them to every frame lets the model cheat by tracking progress directly. Following Jason Ma's generative value learning paper, we give positional embeddings only to the 1st frame to prevent cheating. In the paper, we quantitatively analyze reward function performance in great detail, but here we show a qualitative example from MetaWorld on unseen tasks. These confusion matrices show the dense reward given by each baseline reward model for videos of every unseen task on the rows and the language instruction of all unseen tasks in the columns. Because we want the correctly paired instructions in videos to have the highest reward, the goal is to have a solid diagonal blue line, and none of these baseline methods do. And now here's ReWiND's confusion matrix. ReWiND is able to best distinguish among different tasks and give the highest reward for the correct unseen task. And not only that, it also works for unseen tasks in the real world. Then we evaluate policy learning with ReWiND on new unseen tasks in MetaWorld. ReWiND policies outperform baselines in success rate across 8 unseen tasks with image-based offline to online reinforcement learning. We also perform real-world RL on a low-cost 30 Hz bimanual manipulation setup, where ReWiND enables real-world learning of unseen tasks in just 1 hour of total experiment time. We compare against VLC, one of the best performing reward baselines on our reward analyses, and an offline RL pre-trained with VLC reward labels doesn't perform well on these unseen tasks, and online RL doesn't help improve that policy. While ReWiND's pre-trained policy performance is similarly poor, but it greatly improves after real-world online fine-tuning.
And to qualitatively demonstrate what policy improvement after just 1 hour of ReWiND training looks like, here's the pre-trained policy performing the task of putting the orange cup into this tall box. So the policy would typically either miss the grasp, like you see here, or if it grasps it, it's unable to actually bring the cup over the top of the box. Then, when we train online with ReWiND, we again see early failures during training, but over time, our policy learned to slow down, to carefully grasp and lift the cup super high to guarantee making it over the box's edge. To wrap up, we'll just play this video of real-world training over an hour to show it learns this towel folding task autonomously. Here's a QR code of our paper, and I would like to mention that one of the first authors of this work, Yusen, is applying to PhD programs this year. Now we will happily take questions. Thank you.
Great, thank you very much. For questions, please use the microphone closest to you. And can I have the next speaker get set up while we're waiting for questions? Looks like you did such an incredibly good job of explaining that nobody has any questions. That's fantastic. Thank you very much.